Thank you very much. Thanks a lot for inviting me. Right, so I will talk about tensor decomposition and how to do that with sum of squares relaxations. This joint work with based on two joint works with the authors of the Union are Sam Hopkins, Teng Yuma, Jonathan Shi, and Cyril, who is in the audience. Okay. So let's start with saying what's a tensor. So tensor is a very simple object, just an array of numbers where you have multiple indices. Okay? And this generalizes in a natural way vectors where you have one index and matrices where you have two indices. Okay? So more formally, if you have a 3 tensor over RT, then it's a linear combination of these kind of guys, and these are just triples of basis elements of RD, and so that's how the space of tensors, how the space of 3 tensors over RD looks like. And there are special tensors which will play a crucial role in this talk, and those are called product tensors or rank 1 tensors, which come from a single triple of vectors in the underlying space, A, B, and C here, and the coefficients of the tensor that they specify, they depend depend in this multilinear way on the coefficients of A, B, and C in the standard basis. Just like here, and maybe one remark. So sometimes in the literature about tensor decomposition, there's an effort to distinguish between tensor products and chronicle products and other kind of products. But the reason is a bit mysterious to me. So in this talk, this here will be the usual chronicle product for matrices. Will be treated like the usual chronicle product for vectors and matrices. Okay. Now, why should we care about tensors? It turns out that tensors are like a natural shape of data. They arise in many different contexts. In particular, if you have a multivariate distribution and you look at its moments, then this corresponds to it's in a natural way a tensor over the space where the distribution is of the distribution. And similarly, if you have a multivariate polynomial, then the coefficients of that multivariate polynomial form a tensor. Finally, if you have a quantum system that is composed of different parts, then each state of this quantum system lives in a tensor space over the states for the individual parts. Okay? So in that sense, tensors are pervasive data structures, and so the final evidence for that claim is the fact that if you look at this new deep learning software library, it turns out that their very basic data structure is tensors. And so in some sense, these software libraries are just libraries to manipulate tensors in simple ways. Okay, and so this gives rise to the thesis that tensors are the new matrices. In the same sense that matrices were able to tie together a wide range of diverse disciplines. Tensor have the same ability. Okay, but it turns out that tensors have some unique advantages over matrices. So just because they are richer. In particular, there's a reason why these software libraries are not based on matrices, but they are based on tensors. So our tensors are deeper than matrices. And that also means that if tensors are the new matrices, then we should it's the time for to develop algorithms for the tensor age. So we have to identify the algorithmic challenges that come with trying to deal with tensors. And here the hope is to repeat some of this dramatic success that we had for developing for algorithms for matrices in the last couple of centuries. We've seen amazing algorithms for matrices which had dramatic impact in many ways, and the hope is to repeat some of that for tensors. Okay? And again, there will be some unique challenges in doing that, and we'll discuss some of those. Okay. So the problem I want to focus on is tensor decomposition, which is arguably, one of the most fundamental problems about tensors. So suppose you have a 3 tensor. What you want to do is you want to explain this 3 tensor in the simplest way possible. Okay. So with as few vectors of the underlying space as possible, and then the kind of explanation that we look for is these kind of multilinear explanations. In particular, we want to find as few vectors ai, bi, ci as possible, such that the tensor T is a sum of the rank 1 tensors corresponding to ai, bi, and ci. Okay. Now, why would you want to do this? So it turns out that, so as I alluded to before, there are some key advantages that tensors have over matrices. And the key advantage that they have in this context is that if you look at factorizations for matrices, then they suffer from the rotation problem. And what this means is that if you have some low-rank factorization of the matrix, then you can generate very different-looking factorizations just by transforming the vectors with some arbitrary invertible linear operation. Okay, and that means that there's really no sense in which, and in a sense, the matrix factorizations are very non-unique. And in contrast, it turns out that tensor decompositions are often unique. Okay, and this is very important for in applications for tensor decomposition, because so if your idea is to use this decomposition in order to explain the data in the simplest way, you somehow hope that this explanation has something to do with some truth that you're trying to find. And now if the solution is very undetermined, like for matrix factorization, then it becomes not clear what it means that you find a good explanation. But if you find a low rank tensor decomposition and it has this property that's unique, then the vectors that you find, they probably tell you something inherent about the data that you have. Yes?
I'm a little confused about the analogy. You say M equals AB transpose. So, I mean, isn't the right thing to compare, where M is a sum of tensor products or outer products?
Yes, that's the same thing. So, if you look at
rectangular matrices.
Yes, yeah. Here you have rectangular matrices. Maybe I guess it's never clear to me if it's the columns or the rows of A or B.
There's like K by N and N by K if it's rank K, you're saying?
Yes. So here the inner dimension will be R, and that's the same thing that you're trying to minimize.
Okay, so it's just not written in the same way.
Here I think the rows of A and the rows of B will be the vectors that you're the columns of A and the columns of B will correspond to AI and BI in this picture. Right. Yeah, good question.
But I'm still a little confused about why you see these cases as so different, though, because I mean, certainly the singular value decomposition, if the singular values are distinct, gives a pretty unique way to.
Right, but then, if you talk about singular values, then you have in mind that the vectors that you're trying to find should be orthogonal. Okay. And then you're right that if you sort of know a priori that my vectors are orthogonal, then that fixes or that makes the decomposition sometimes unique. Okay, for matrices. And actually, so then you also assume that the singular values are all different. And in the tensor case, it turns out that it can capture. You don't have to assume anything about orthogonality of the true explanation that you're looking for. Okay, and orthogonality, of course, in some contexts is perfectly justified, but in many contexts it's not. But I know, so this advantage comes with the challenge, and the challenge is that tensor decompositions are NP hard to compute in the worst case, and that means that we can't hope to have the same kind of very simple theory that we had for computing matrix factorizations or other matrix problems. Okay, but certainly it doesn't mean that we can't hope for good algorithms, because there are many cases like for example, the story about approximation algorithms, where we have NP-hard problems, but we managed to find interesting ways of dealing with them, finding provable algorithms for them. And so the hope is to do that we can do the same thing for tensor decomposition. And it turns out that this hope is seems to be justified. There's some evidence that indeed we can have very good algorithms for these kind of problems. And another nice thing is that the tractability of this problem seems to go hand in hand with the uniqueness of the decomposition. Okay, so there's some apparent relationship between these properties. When is it tractable to find tensor decomposition, and when is it unique? And so in this talk, we will see how these things are indeed related. Okay, and just to give you more examples, so it turns out that indeed, efficient algorithms for tensor decomposition, they gave rise to provably efficient and also practically efficient algorithms for a wide range of learning problems. All the problems are listed here, and in general, these unsupervised learning problems, they ask you to cluster some observations in a particular way, and it turns out the best provable algorithms for these problems are based on tensor decomposition. And it also means that if you have better algorithms for tensor decomposition, it means that you can learn these problems, or you can solve these learning problems better. Okay, so now to give you some, I want to sort of show you what is known about the algorithmic difficulty of the kind of algorithms that we have for tensor decomposition. And it turns out that it's convenient to think about tensor decomposition in a slightly different way, in a sort of a probabilistic way. And this way, on some level, the notation is a little bit more familiar. And it turns out that also our algorithms they follow this viewpoint. Okay, so now consider this problem. So it's an inverse problem. And what you're trying to do is you're just given some moments of a distribution, and you're trying to find what's the original distribution. And so what's the precise setting? Suppose that we have some set of vectors a1 up to an that are unknown, and we are given the low degree moments of the uniform distribution over these vectors. Okay, so the first k moments of this distribution, and our goal is to recover the original vectors. Okay, so this is a special case of the multivariate moment problem. And it's just a reformulation of the tensor decomposition problem. And our question is, under what conditions on the vectors a1 up to an and the number of moments k that we observe, can we solve this problem efficiently and robustly? So robustly means that even if there's some error on the moments that we observe, we want to be able to solve this problem. Okay. And there's a classical case which has its origin in the 1970s in a paper by Harshman, an algorithm attributed to Jenrich. And this case is when the vectors a1 up to an are linearly independent. Okay. Notice that it also means that n is at most d in this case. It turns out that if they are linearly independent, you can, without a lot of generality, assume that they're actually orthonormal. Okay. So orthogonal unit vectors. The reason is that if you get the first 3 moments, let's say, of this distribution, then the second moment matrix allows you, to construct this linear transformation, and this linear transformation orthonormalizes the vectors. Okay, so you can just push this linear operation into everything that you observe, and then, effectively, that allows you to assume that the vectors are orthonormal. And in this case, you can solve the problem, as good as you could hope for. So it turns out that 3 moments are indeed, the first 3 moments are indeed enough. There's a very simple spectral algorithm based on diagonalizing matrices. And it's a really nice algorithm. I will explain it later in the talk because we will use it as a subroutine. Now, one interesting question here is what happens if there's noise in the input? Suppose that our input is not the sum of the rank 1 tensors of the AIs, but there's some error tensor E added to it. And so now you can ask, when is it information theoretically possible to still solve this problem? Turns out that if the injective norm, which is an analog of the spectral norm for tensors, if this is much less than 1, then you can still solve the problem. You can still approximately recover the vectors a1 up to an. There is a polynomial time algorithm based on some non-convex gradient descent ideas called tensor power iteration, which solves the problem whenever the injective norm is at most 1 over n. Okay, so there's this gap of 1 over n between the thing that is information theoretically possible and what we know to do in polynomial time. And in this talk, this color looks different here, we will give a polynomial time algorithm based on the sum of squares idea, which I will define later, which shows that you can solve the problem whenever some other norm, the sum of squares norm of the error, is at most is much less than 1. So what is this norm? So this norm is an efficient relaxation of the injective norm. And it turns out that it satisfies that, for every error tensor, the sum of squares norm is at most square root n times the injective norm. And that means that this result actually dominates. So this condition is satisfied more often than this guy. Basically, there's a difference between these two conditions. There's a gap of at least root n. And it turns out that if you know that the error is random, let's say chosen from a independent Gaussian distribution, then the sum of squares norm is at most n to the 1/4 larger than the injective norm. Okay, that means that there's only a gap to n to the 1/4 to what's information theoretically possible. And this and there's some evidence that indeed, like, you can't. It is difficult to improve over this n to the 1/4. In particular, even if the number of components is just 1, then we don't know better algorithms for that. And if the number of components is 1, so n is equal to 1, and you have a random error, this corresponds to a stochastic model for tensor PCA, which was proposed by Montanari and Richard. Okay, and so this bound here actually is the best. Also, is the best that we know, even if n is equal to 1 for random tensors.
So,
okay. Yes.
To the positive side, your result is under what assumption on n?
So positive side, so they are orthonormals, which means that n is at most d. But yeah, n can be equal to d. That's right.
Just to clarify,
yes?
the goal is to reconstruct the vectors exactly.
So that's a good question. So if you have noise, if you have some error in the input, then you can, the accuracy which you want to recover the vectors, it depends on how large the noise is, and these thresholds that are stated here, they are the case when you can recover the vectors up to 0.9, 0.9 of their mass. So these are unit vectors. So if if this is the case, then you can get an epsilon approximation for the vectors. Yeah, that's a good point. Okay. So this, and now for the rest of the talk, I will ignore this issue about noise most of the time whenever it's okay. But just as a remark, so there's a sense in which these algorithms based on sum of squares, they are almost automatically robust to noise, which is a nice feature that many other algorithms don't share. Now, a more general case is instead of linearly independent vectors, is to consider random vectors where n is much larger than d. Okay, so it's strange. Why do I say that this is a more general case? This is a more general case because if you have linearly independent vectors, by what we said, we can assume that they're orthonormal, and if they're orthonormal, you can apply a random rotation to them. Okay, and now if you apply the random rotation to orthonormal vectors, you basically have random unit vectors. So it means that there's a way of reducing the linear independent case to random vectors with n less than d. Now we ask, what happens if you have random unit vectors with n much larger than d? And suppose you only want to use the first 3 moments of the vectors. So this problem has been studied only very recently, and so it turns out to be quite a bit harder than the case of linearly independent vectors. And the first result in this context is that if you have at most c times d for some constant c bigger than 1 vectors, then there's an algorithm that can solve the problem with a running time that is exponential in c. So this is reasonable if c is logarithmic in D. And another algorithm, so this is just using a spectral algorithm, and then this non-convex gradient descent type algorithm. It turns out that even if the rank is d to the 1.5, if you have d to the 1.5 vectors, you can show that this algorithm has some local convergence guarantee, in the sense that if you start very close to the solution, then the algorithm finds the solution. But this doesn't correspond to like an efficient algorithm, because it's not clear how to get close enough so that this local convergence plays a role. And then the first algorithm that sort of worked for significantly larger number of vectors, actually matching the bound for the local convergence of tensor power iteration. It was based on sum of squares, and it solves the problem in quasi-polynomial time, so which is a bit larger than polynomial time, but still an interesting guarantee. And in this work, okay, so the question now is, can you solve this problem if the rank is some polynomial factor larger than d in polynomial time? Okay, and in this talk we show that this is indeed the case. So there's an algorithm based on sum of squares which works up to the same bound for the rank as before, but runs now in polynomial time. And actually, the precursor of that result is a result which works up to something that is still polynomially larger than d, a rank that is polynomially larger than d, and it has the nice feature that it's much faster than it's sort of an algorithm that is reasonably fast. It runs in time, at most d to the 3.33, and notice that this is pretty close to linear time because the input has size d cubed. Now, going to more general kinds of vectors. So we talked about linear independent vectors, random vectors. Now, another model that people studied is smooth vectors. So in this falls into the framework of Spinozan of smooth analysis. And here the idea is that usually in smooth analysis the idea is to perturb the input and hope that you can solve the problem on the perturbed input. Now, it turns out that for these kind of inverse problems, you want to do it a bit differently. So here the idea is that you perturb in some sense the solution that you're trying to find. You perturb the vectors, and this induces, of course, the perturbation of the tensor, which the algorithm gets as input. But it's a very structured kind of perturbation, and then sort of the algorithm gets this structurally perturbed tensor t, and is trying to recover the vectors. And here, nice thing is that the amount of perturbation that we apply to the vectors is extremely small. It's just, if they are unit vectors, then we perturb it by some polynomial amount. We add, a Gaussian of, some inverse polynomial length, and this can be, as small as you like. And here the, first result is that, from 2007, there's a polynomial time algorithm that works if you have the first 4 moments, and it works up to rank at most d squared. Okay, and the nice thing is that on some level I only care that this is larger, polynomial factor larger than d, and it's a somewhat mysterious algorithm that combines in a very ingenious way solving large systems of linear equations and this idea of these spectral techniques from earlier algorithms. But one unfortunate aspect of this algorithm is that it assumes that you have access to the exact moments, and in particular it's not known whether it tolerates a polynomial amount of noise. And in many applications, in particular for these learning applications, you really need to be able to tolerate a polynomial amount of noise if you want the algorithm to run in polynomial time. And that motivated sort of a later paper by Bhaskar et al., which showed that if you have more moments, up to first 5 moments, then you can have the same guarantee as this algorithm, which is called the Fubbi algorithm. But in addition, you can tolerate a polynomial amount of noise. Okay, and in this talk, we will the techniques explained in this talk. They allow you to sort of combine the benefits of both of these results. It shows that indeed 4 moments are enough if you want up to this rank, and you can still tolerate a polynomial amount of noise. And again, this uses sum of squares. And the nice thing about this part is that the key ingredient here is to to interpret the earlier algorithm, this Fooby algorithm, as falling into the sum of squares, as a special case of the kind of sum of squares algorithm that have been proposed before. Okay, so it turns out that on some level, this algorithm here it falls into this sum of squares framework. Okay, finally, what can we do if we don't make any assumptions about the vectors? Suppose that we have completely general unit vectors, and just for simplicity, assume that we put them into isotropic position. Okay, so now, I told you before that this problem is NP hard, so somehow, you would expect that you shouldn't be able to do anything for if you don't make any assumptions about the vectors. But it turns out that, if you are in this viewpoint in terms of these inverse problems, then it still makes sense to ask this question, because so what we do is we fix the vectors. Now we ask how large do we have to choose the number of moments in order for us to be able to recover the vectors. Okay. And it turns out that if you're willing to spend quasi-polynomial time and you want to recover the vectors up to some accuracy epsilon, then if you get moments up to degree 1 over epsilon times logarithmic in this ratio n divided by d, then you can recover the vectors. And this algorithm is based on sum of squares. And this, the techniques in this talk, they allow you to do the same, achieve the same guarantees, but with a polynomial time algorithm. And this has also some applications for dictionary learning. Okay, so let me see, what's the time? Okay, great. Okay, so now I'll try to give you some of the ideas from the proof. And so first, let me explain this very first, this very classical algorithm that works for linearly independent vectors. And this is an algorithm due to Jenrich. So we have access to the first 3 moments. And as I explained before, if you have linearly independent vectors, we can actually assume that they are orthonormal, because the second moment allows us to orthonormalize them. Okay, so now what can we do? Well, we look at the third moment. So this is like a 3-dimensional array of data and of numbers. And now what we'll do is we will choose a standard Gaussian G. In dimension d, and we align this Gaussian, in this way with our 3-dimensional array of data, and we will use it to, take a linear combination of the slices, that is as sort of is suggested in this diagram, and this will result into a 2-dimensional array now. This is a matrix, and the algorithm, it turns out, will just look at the eigenvectors of that matrix. Okay, and now this operation is called a contraction, because you contract one index using this vector g, and now before you had 3 indices, and afterwards you only have 2 indices, and as the linear algebra operation is just that you multiply you apply this linear transformation to the 3 tensor the third moments, where you don't do anything to the first 2 indices, and you apply this linear functional G transpose to the third index. And the resulting matrix, let's not worry about exactly how this works. It looks like this. So it's a weighing of the outer products of the vectors AI, and the coefficient is the inner product of the vector G and AI. And now, because we orthonormalize the vectors, these guys will be eigenvectors of the matrix. And the eigenvalues are those coefficients. And because G was a random vector, and the vectors AI, they are orthogonal, these are actually independent Gaussians. And that means that with probability 1, they are all distinct, and they're also reasonably far apart. And that means that if you compute the eigenvectors, that each eigenspace is 1-dimensional, corresponding to one of the AIs. Okay? So that's great. And now the challenge is, suppose that we want to do this if the number of vectors is much larger than I mentioned. And now the issue is clearly that even if you do this operation, then it can't be the case that each AI is an eigenvector of the matrix, because we just have d eigenvectors, but we have so that doesn't work if we have more than d vectors. Okay. And so here's the approach, the general approach for dealing with overcomplete 3 tensors. So we have we have as input this 3 tensor, and now we imagine that we have some magic procedure that allows us to compute given the three moments, third moments, it allows us to compute the 6 moments of the distribution. Okay. Now, why would that be good? Well, if you look at the 6th moment of the distribution, you can think of it as the third moment of the uniform distribution over A1, tensored with itself, up to AN tensored with itself. Okay. And now these vectors, if you choose A1 up to A at random, then these vectors, they essentially look like random unit vectors in d squared dimension. And this this is good because we have the number of vectors that we have here is much less than d squared, and if I choose at most d squared random vectors in d squared dimension, then they will be very close to orthogonal, and in particular these guys, they are close enough to being orthogonal for Jenrich's algorithm to work. Okay, so if you just apply Jenrich's algorithm, do this random contraction, then it turns out that the eigenvectors that you will get, they will be very close to these guys, and from these guys I can recover the vectors A1 up to N. Okay, so that's the plan. Okay, what's the weakness of the plan? The weakness is that we assume this magical procedure that allowed us to lift the third moments to sixth order moments. And to get some intuition about how we could go about constructing this kind of magical procedure, let's consider the following ideal implementation. Which will not be efficient, but it will sort of guide us to the right thing to do. And so, what would be an ideal implementation of this magic box? And so the ideal implementation I want to consider is the following. Suppose we will this magic box. It computes a distribution d over the unit sphere, which has the same third moments as the given third moments, and then it just outputs the 6 moments of the distribution that it computes. Okay. So what we would want to show here is that if you do this, if you do this search over distributions that have the same third moments as the given third moments, what we want to show is that this will result into a distribution that has whose 6th moment is close to the true 6th moments. Okay. And notice that one key aspect of this box is that we somehow have to, in some sense, the existence of this magic box, it relies on the fact that the third moments determine the 6th moments, right? And that's by itself is a non-trivial fact, which is only which will use the fact that the vectors are random. Okay. Okay, not sure where that's here again. Sorry. So let's prove the fact that let's prove this claim that the 6 moments of the distribution that we computed in this way, they will be close to the 6 moments of our vectors A1 up to N. So first of all, there are some equations that follow from the fact that the third moments of the distribution D is the same as the third moments of the vectors A1 up to N. So first of all, if we take the inner product of the third moments of M of the vectors with itself, then this will be a number roughly 1 over n, and but if this guy has the same moment as the same third moment as this, then these two inner products have to be the same, and this inner product, it turns out to be the expectation under distribution of this polynomial normalized by 1 over n. Here the conclusion of this is just some computing consequences of this equation. The conclusion is that the distribution D, it satisfies the property that under distribution D, this polynomial has expectation very close to 1. Okay, and now if you look at this polynomial, it turns out that with high probability over the vectors, over the choice of the vectors A1 up to N, the way this polynomial looks like, as a graph on the sphere, it looks like this. So the only points where the polynomial is large are at the points A1 up to AN, and everywhere else it's very close to 0. And that means that that if the distribution D satisfies this property, that under distribution D the expectation of this polynomial is close to 1, it means that essentially the distribution has to be supported on vectors very close to A1 up to AN. Okay, so in this sense, and that means if the distribution is indeed supported on the essentially supported on these vectors, it also means that if we look at this polynomial, where we raise the inner products to the 6, this will also be very close to 1 in expectation under the distribution. just because if you plug in each of these vectors as u here, you will get something that is essentially 1. And now we can do this sort of the reverse calculation that we did here. Here we showed that the fact that M3 is equal to the third moments of D, it implies that this is large. Turns out that this is essentially some equivalence, and then if you go backwards, this now implies that the sixth moment of the vectors are close to the sixth moments of the distribution that we computed. Okay, and that's what we wanted. Okay, great. So now we showed this claim that the sixth moments of the distribution that we computed is close to the sixth moment, the true sixth moments. Now there are two remaining questions. One question is, this ideal implementation is not efficient because we, pretending that we could search over these distributions. So we have to somehow find a, efficient way of doing that. Second question is, the kind of error that we have here, it should be the case that Jenrich can tolerate this error. Okay, because, now we feed, this kind of thing which is only close to this, we feed it to Jenrich's algorithm. So, Jenrich's algorithm should be tolerant enough to cope with that error. So it turns out to be a principled way of dealing with the first question. It turns out that instead of optimizing over all distributions, we can optimize over a more general set of objects called pseudo distributions, and this comes from the sum of squares framework. Okay, so that sort of deals to some extent with the first question. The second question, can Jenrich tolerate this kind of error? So here the answer turns out to be no. The error is too large. Okay, so that's the problem. So what do we do? Well, and you can sort of see it. What's the problem, right? Because if you sort of remember the calculation that we did here, we essentially showed that these two guys are close in Euclidean distance, but Jenrich's algorithm relies on eigenvalues, magnitudes of eigenvalues, and that means that or these spectral gaps, and it means that if sort of this kind of error that we have here, it can sort of contribute a small number of very bad eigenvalues, and that will break Jenrich's algorithm. And in some sense, this is a problem because we don't really have any. Because we sort of think of implementing this magic box as sort of this kind of search, we don't really have much control over what kind of distribution we get from this box. And here the idea is to add an additional constraint to the search, which is similar in spirit to a maximum entropy constraint. And so what we want is that if you look at the spectral norm of the fourth moment of the distribution D, this should be small, as small as you can hope. In some sense, this would be as small as the spectral norm of the fourth moment of the fourth moment of the vectors A1 up to An.
What do you mean by the spectral norm of the rank 4?
Yeah, that's a good question. So here, reshape it as a d squared by d squared matrix. Yeah, but of course, I should have. I was hoping no one will not.
David.
Yes.
Can there be very different distributions D that match the?
Yes. Yes. I mean, if I just tell you that the distribution satisfies this property. Okay. So if that matches exactly the third moments. Yes. So even if I just tell you this property, it's you can take any. For example, you can take the true distribution, over uniform over A1 up to N, and then add some adversarial but small error to each vector AI, and it will still satisfy the property. And if you add an adversarial error to each AI, for example, you could choose it such that it's the same. You add an error in the same direction for every AI, and this will contribute a very large eigenvalue in every sort of resulting computation.
But if it matches exactly, there can be only one solution.
Then, I don't know. That's a good question. I don't know how to exploit the fact that it matches exactly. That's a good question. Yeah. I would doubt that it makes a big difference. Okay. Because on some level, we're not on some level. Even this ideal implementation, it's not doing the right thing, right? Because the really right thing would be to look only at distributions that that are distributed over n vectors that look like random vectors. Okay. So to search over every distribution that looks like the kind of distribution that we are assuming. And the fact that we are we're looking at an arbitrary distribution over the sphere and just require the third moments match, it leaves a lot of freedom.
But with the maximum entropy constraint?
With the maximum entropy constraint, it's sort of, so in some sense, this maximum entropy constraint, it doesn't really improve the errors that we have, but it turns out that this allows us to control the effect of the error for Jenrich's algorithm at the end. And I hope that I can show this. So, okay, so what are, so now the only thing that we have to do is we have to deal with these two kinds of questions. So let's deal with the first question. So instead of optimizing over all distributions, we optimize over pseudo distributions. And on some level, okay, so let me just, so pseudo distributions are generalization of actual distributions where low complexity events behave like you would expect. They have no negative probability and everything is nice. But all bets are off if you have high complexity events. And the notion of low complexity and high complexity events is sort of specific, and it will, of course, we'll see it next. So formally, degree D pseudo distribution is just a function on the sphere, and such that if you, let's say, finitely supported, such that if you sum up the values of the function, you get 1. Okay, that's what you would expect from a probability distribution. And but it's not a non-negative function, not necessarily a non-negative function, but it has the property that if you take if you look at the inner product of the function d with any square of a low degree polynomial, this will be non-negative. Okay, so these are the simple events that have non-negative probabilities. And it turns out that if you sort of change the degree requirement here for the functions, then you get smaller and smaller sets. And if you choose if you allow here, if you allow functions of arbitrary degree, that would imply that the function capital D is non-negative everywhere. So it means that really corresponds to uniform distribution, but everything intermediate is a more general object. Now we can formally define an expectation under this pseudo distribution D, just like we would for actual distributions. And now the advantage of pseudo distributions is that unlike for actual distributions, we can optimize over these distributions over these more general distributions efficiently. Particularly, there's a separation oracle which runs in time d to the k for the convex set of pseudo distributions. And this means that if you have basically every optimization problem that you would like to solve about distributions, you can solve it efficiently for pseudo distributions. Okay, so maybe that's like as a take-home message. If you ever encounter, feel yourself, if you ever are in the position of wanting to optimize over distributions, but it's not clear how to do it, then just you can try to optimize over pseudo distributions, and with some luck it will work just as well. Okay, it turns out that this idea of pseudo distributions it's a way of capturing the best known polynomial time algorithms for a large class of problems. So on some level, like this is the best efficient way of relaxing distributions that we know of.
So one question.
Yes.
Every time I've seen this, there is never. Is the finitely supported assumption? You can always make the finitely supported assumption.
Okay. So here I did it just because I didn't want to write integrals. Of course, if I'd make this assumption, it's not really convex, right? Because only sort of like the limiting object will be convex. But yeah, it will not. I just wanted to avoid dealing with measure theory issues. But finally supported. So, because on some level you can assume that these functions are really this function capital D. You can assume that it's a degree. It has degree at most k. So it's a low degree polynomial, and then and that sort of means that you can specify it as a finally supported distribution, a finally supported function. Okay, so maybe let me skip this. Okay, so this is so there's a notion of sum of squares proofs, which is an abstraction of the kind of properties that hold for pseudo distributions, that are true in the real world and also hold for pseudo distributions. Let's now not go into that. So one thing that now what we want to do is before we said that we saw a proof that if you have an actual distribution whose degree 3 moment is the same as a degree 3 moment of our vectors, then the degree 6 moment is close to the degree 6 moment of our vectors. And if you recall that proof, actually the only thing that we used is the fact that if this polynomial has large expectation under D, under distribution D, then also this polynomial has large expectation under D. And that means that on some level we just have to prove that this inequality is still true for pseudo distributions, and this can be done. And it boils down to proving bounds on the spectral norm of these kind of matrix polynomials, which are unfortunately we don't have good general tools for doing that, but it turns out that for this particular matrix polynomial we can prove good bounds on its spectral norm. So this addresses the first issue, trying to replace the search over distributions with search over pseudo distributions, and so this means that nothing changed. Now the second issue, it's in some sense an orthogonal issue, and here we want to say that this additional constraint that the spectral norm of the computed distribution of the moments of the computed distribution is small. This allows us to say that Jenrich still works. And the way we will say this is that we'll show that if you do this random contraction, then the top eigenvector of the resulting matrix will be close to one of the vectors a sub I. And okay, so maybe let me just show you on a high level what's happening. So if you do this random contraction, you can think about it as doing a random contraction in the direction AI, and a random contraction orthogonal to the direction AI. Okay. And now, so that means that this random contraction, it naturally sort of decomposes in something parallel to AI and something orthogonal to AI. And it turns out that the condition that our moments are close in Euclidean norm to the true moments, this allows to show that this behaves nicely. And the fact that that we have this entropy constraint, it allows us to show that this orthogonal part behaves nicely. Okay. And now what you want to, let me sort of skip the calculation here. I think I'll also skip all of that. So this was okay. So maybe just a word here. So one unfortunate aspect of this algorithm that I described is that it uses this. It optimizes here over pseudo distributions, which is a very slow process in general. And you would like to have this also do this fast. And it turns out that on some level, what you wanted to do here is not. You didn't want to. The only thing that you want to do is to find an object here that fools Jenrich's algorithm, that behaves like a true 6 moments to Jenrich's algorithm. And it turns out that you can do to some extent implement this kind of procedure in a very simple way, just as a polynomial of the input tensor, as a low degree polynomial of the input tensor. And this object here turns out to be a polynomial, a degree 3 polynomial in the input tensor. And this turns out to fool Jenrich's algorithm in the same sense that the moments of the distribution that we computed before fooled Jenrich's algorithm. And this gives a fast algorithm. In particular, it runs in time d to the 3.33. Okay, I can also skip that. Let me conclude. So we saw a way of using sum of squares for tensor decomposition, and there were two parts here. One was to use to give a sum of squares, to give a proof that is so valid for pseudo distributions, which shows that the third moments determine up to some small error the 6 moments. And the second part was to show that the Jenrich's algorithm can be used as a rounding algorithm for the kind of pseudo distributions that are computed by sum of squares. And then there's a way of obtaining fast algorithms from this sum of squares viewpoint by instead of computing pseudo distributions, it's enough to compute some low degree matrix polynomial of the input, which with aim of fooling the rounding algorithm that that we had here. Two open questions. So one is so what we saw is a way of decomposing random 3 tensors where the rank is at most d to the 1.5. So this d to the 1.5 is a bit mysterious, but it seems to be like the right answer in the sense that, in the following sense, so it is possible information theoretically to decompose random 3 tensors even if you do even if you have n squared d squared vectors. Okay, but it seems to be that going beyond d to the 1.5, you run into some inherent computational complexity issues, and it would be nice to formalize this feeling. And the final thing is that, so when we talked about the smooth analysis for tensor decomposition, we saw that there's a way of doing 5 tensors and 4 tensors, and it would be great to be able to also have a smooth analysis for overcomplete 3 tensors. Okay, and on some level that would be a great strengthening of our result for overcomplete for random overcomplete tensors. Okay, thank you very much.
Questions?
Thanks again.